Chemical energetics. The first thing in chemical energetics is exothermic and endothermic reactions. So exothermic reactions, and in exothermic and endothermic reactions, it's basically making the energy profile diagrams. Exothermic reactions are those reactions in which heat is given off, and when we make the energy profile diagram, this is the energy in kilojoule per mole, this is the progress of the reaction. So in exothermic reactions, since energy is given out, so the energy of the reaction, energy of the reactants is more than the energy of the products, which is why the reactants are above the products. This arrow represents enthalpy change, and in exothermic reactions it is negative, that is shown by the downward arrow, and this is the energy of activation, which is always positive. In endothermic reactions, the energy of the reactants is less than the energy of the products, because in endothermic reactions energy is being absorbed into the products. So the energy profile diagram is somewhat like this. This is delta H, and it's positive, shown by the upward arrow, and this is the activation energy. Now another type of question that can come is of a two-humped graph. In a two-humped graph, a two-humped graph is of a reaction which takes place in two steps. For example, if the reactant is X and the product is Z, so it's basically going from X to Z. But another way of this could be that first X converts to Y, and then Y converts to Z. So it's a two-step reaction, and in this case the intermediate is Y. So Y is somewhere over here. This is the position where we mark Y. This is the graph. Now over here, as you can see, the delta H of the first hump will be positive. So that means that the first reaction is endothermic, that is positive delta H. And for the second reaction from Y to Z, the delta H is going downwards, that it's negative. So for the second reaction, delta H is negative. So questions can come on this as well. Are the standard enthalpy changes? The first is the standard enthalpy change of formation, represented by delta HF phi. The symbol phi represents that the conditions are standard. That means that room temperature and pressure. Now what is the standard enthalpy change of formation? Its definition is the enthalpy change that occurs when 1 mole of compound is formed from its constituent elements in their standard states under standard conditions. So what does that mean? It means that, for example, if we have to form C2H5OH, let's say ethanol. So the equation for the formation of ethanol will be, it was 1 mole of the compound from its constituent elements. So the elements of this are carbon, hydrogen, and oxygen, forming C2H5OH. Now there are 2 carbons, there are 6 hydrogens over here, sorry, it's OH, 6 hydrogens over here, so 3 over here, and then there's 1 oxygen. So because we have to form only 1 mole of the compound, so it has to be half oxygen. Similarly, if it was H3PO4, we would have hydrogen plus phosphorus plus oxygen, forming phosphoric acid. Now there are 3 hydrogens over here, so we'll multiply this with 3 upon 2. There's 1 phosphorus, and then there are 2 oxygens. There are 4 oxygens, so 2 O2. This was the standard enthalpy change of formation. Now, next is the standard enthalpy change of combustion. The definition of this is the enthalpy change that occurs when 1 mole of the compound is completely burned in the presence of excess oxygen under standard conditions. So again, over here only 1 mole of the compound is being burned. So for example, if we have to write the equation for the combustion, the standard enthalpy change of combustion of, for example, carbon dioxide. One thing I forgot, we can write, we write over here delta HF5 because it is the standard enthalpy change of formation. Now for carbon dioxide, we have to form the standard enthalpy change of combustion, sorry, not carbon dioxide, carbon. Carbon dioxide won't be combusted, so carbon. So for carbon to be combusted, 1 mole of the compound has to be combusted in excess oxygen. So carbon plus oxygen forms carbon dioxide. Similarly, if it's, for example, hydrogen, so 1 mole of the compound has to be combusted, so H2 plus O2, this will form water. So we'll write half over here. Now in these two equations, this is the delta HC, delta HC. What we can note over here is that if we look closely, so this equation can also be called the equation for the standard enthalpy change of formation of carbon dioxide, because over here 1 mole of carbon dioxide is being formed from its constituent elements. So from this we get that delta HF5 of carbon dioxide is equal to delta HC5 of carbon, or you can write graphite, whatever. It's carbon. Then from here you can see that 1 mole of H2 is being formed, so this can also be called the equation for the standard enthalpy change of formation of water. So from here we get that formation of water is equal to the combustion of hydrogen. These will help us in numericals. The last enthalpy change is the enthalpy change of neutralization. It is defined as the enthalpy change that occurs when an acid and an alkali react to give 1 mole of water. And for this, the basic example could be that there is the ionic equation for neutralization. This forms 1 mole of water. So the enthalpy change over here is delta Hn. Now in chemical energetics, there are a lot of different types of numericals. So we'll take each of them separately, and if I get time, then I'll do past papers for them, a few examples. So the first concept that we have is the Hess's law of constant. In this, what we basically have to know is that if, for example, there's a reaction, there's a one-step reaction that is sodium hydroxide and carbon dioxide react to form sodium carbonate plus water. And for example, the delta H for this reaction is X. Now this reaction can also proceed through 2 steps. The first step would be that sodium hydroxide reacts with carbon dioxide to give sodium hydrogen carbonate. Delta H for this, let's say, is Y. Step 2 is that the sodium hydrogen carbonate reacts with NaOH to give sodium carbonate and water. And let's say the delta H for this is Z. So even if the reaction proceeds in one step, or by 2 steps, the total energy change will be the same. That means that this is Z. That means that the energy change if it's a 1-step reaction is the same as the total energy change if it's a 2-step reaction. I hope that makes sense. The first kind of numericals are when we have to find the enthalpy change of combustion or neutralization, and we have some data about how the reaction heated water and how the temperature of the water changed. So over here the main formula we use is Q equals mc delta T. Q is basically enthalpy change, delta H equals mc delta T. C is specific heat capacity, that is 4.18, it is given in the data booklet, and M will be the mass of water, because water is being heated, and this is the temperature raised of the water. Now I have a question for standard enthalpy change of combustion, so we'll do that. In an experiment to determine enthalpy change of combustion of ethanol, 0.23 gram of ethanol was burned and the heat given off raised the temperature of 100 gram of water by 16.3 degrees Celsius. So there is 0.23 gram of ethanol and it's raising the temperature of 100 gram of water by 16.3 degrees Celsius. Calculate the heat energy change during the combustion of 0.23 gram of ethanol. So we have to find delta H, which they've labeled as Q in the question. So Q equals M was 100, then there is C, that is 4.18, and there is delta T, that was given as 16.3. So 100 times 4.18 times 16.3, 6813, we'll write it as 6810 joules. That was the first part. Second part में they're saying calculate the enthalpy change on burning 1 mole of ethanol. Include a sign in your answer. So they're asking the enthalpy change for 1 mole and they're asking for a sign. Right now the energy change that we found was for 0.23 grams. So if there was 0.23 grams, that means the number of moles of that will be for ethanol. Ethanol is C2H5OH. So we'll divide this by 2 carbons, so 24, 6 hydrogens, and then 1 oxygen. So this is equal to 5 times 10 power negative 3. So for 5 times 10 power negative 3 moles, the energy change we found was 6810 joules. And we have to find the energy change for 1 mole. So if there is 1 mole, the energy change will be x joules. X will be 6810 upon 5 times 10 power negative 3. This is coming equal to 136,200. This can also be written as, this is in joules, this can be written as 1360 kilojoules. And because this is the enthalpy change for combustion, and combustion is an exothermic reaction, so we'll have a negative sign over here. Next are the numericals using bond enthalpy values. Bond enthalpy values are basically the minimum amount of energy required to break 1 mole of a particular covalent bond into gaseous atom. That is the bond enthalpy or the bond energy. Now how do we use them? So basically we have a formula. The formula is that delta HR equals, this sign means summation, bond enthalpy of reactants minus summation of the bond energy of the products. So what this means is that to find the delta HR, the enthalpy change of a reaction, add all of the bond energies of the reactants, subtract from them the bond energies of all the products or bond enthalpies, and you'll get delta HR. So let's take an example. If for example we're given with this equation, Now to solve this equation, there are and you have to find the delta HR for this reaction. To solve this question, there are two methods. If in the question no other data is given, but it just says that use the data booklet, use the bond energy is given in the data booklet to find the enthalpy change of the reaction, then we'll use this formula. And the second method we'll do in a few minutes. That will be the Hess's cycle that we'll do after these numericals. So for this method, the bond enthalpy method, what we'll do is first we'll write all of the molecules in their structural formulas, in their displayed formulas. So for ethanol, and there's oxygen, there are 3 oxygens. Oxygen has a double bond. There are 2 carbon dioxides. And there are 3 water molecules. Now we have to add all of the bond enthalpies of the reactants and then subtract all of the bond enthalpies of the products. So delta HR equals. Now in the reactants, there are a total of 5 carbon-hydrogen bonds. From the data booklet, you'll find the carbon-hydrogen bond की enthalpy change, की bond enthalpy. Carbon-hydrogen bond is 410. There are 5 of them. Next, there is 1 carbon-carbon bond. Carbon-carbon bond is 350. Then there is 1 carbon-oxygen bond. Carbon-oxygen bond is 360. There is 1 oxygen and hydrogen bond, OH, that is 460. Then there are 3 oxygen-oxygen double bonds. Oxygen-oxygen double bond is 496. 3 times 496. This was the reactants की bond enthalpies. Now subtract the products की bond enthalpies. Products में first there are 2. In carbon dioxide, there are 2 carbon-oxygen double bonds, and there are 2 carbon dioxide molecules. There are total 4 carbon-oxygen double bonds. Carbon-oxygen double bonds are given over here. Carbon-oxygen double bonds are 740, so 4 times 740. And then there are 2 OH oxygen hydrogen bonds in 1 water. There are 3 waters, so there are total 6 OH bonds. OH is 460. So if you solve this, you will get the enthalpy change of the reaction. -1012 kilojoules per mole. Now why is this kilojoule and not joule? That is because in the data booklet the energies were given in kilojoule per mole. MCQ I was thinking about discussing. So nitrogen and oxygen can react together to form nitrogen monoxide. This is over here, the delta HR is given. What is the bond energy of the bond between the atoms in NO? So over here they're asking for the bond energy. So firstly, so our formula was delta HR equals summation of bond enthalpies of reactants minus summation of bond enthalpies of products. Over here in the question, delta HR was given as 180. For the reactants are nitrogen and oxygen. There is 1 N2 and one O2. So we'll use the data booklet for that. There's one nitrogen triple bond and there's one oxygen double bond. So in the data booklet, nitrogen triple bond is 944. Oxygen double bond is 496. Then in the products there were two NO molecules. Now in the data booklet, the bond enthalpy of nitrogen monoxide I think is not given. So for this, let's suppose that the bond in enthalpy of nitrogen monoxide is X. So we'll have to subtract 2X from here. Now solving this, 944 plus 496 minus 180. This will give X equals, there is 944 plus 496, 630 kilojoules per mole. That is in this MCQ option A. So in this formula, we have to use this formula when bond enthalpies are mentioned, and any one of the values could be a variable, and you have to find that. Next is Hess's law thermochemical cycle. Over here, this is the last type of numerical and chemical energetics. Over here, we either use the delta, the standard enthalpy change of formation, or the standard enthalpy change of combustion to find the different enthalpy changes of reactions. So I'll take an example from the past papers and then I'll explain. So over here in this question, the table gives some enthalpy change of combustion values. Construct a label energy cycle to show how these values could be used to calculate the enthalpy change of formation for this molecule. So we have over here the combustion data. Now what we know is that from these four molecules, oxygen cannot be combusted because combustion is basically oxidation, so oxygen cannot be oxidized. But the other three molecules can be oxidized. And when these three molecules are oxidized, either carbon dioxide, water, or water are formed. When carbon is combusted, carbon dioxide is formed. When hydrogen is combusted, water is formed. When C3H7OH is combusted, then carbon dioxide and water both are formed. Now, the basic concept behind this method is that whether we go in one step or through multiple steps, the enthalpy change, the total enthalpy change or the net enthalpy change remains the same. So for example, over here what we'll do is that we know that for carbon to be combusted, it will go to carbon dioxide. The energy change for this is negative 393.5. This is the enthalpy change of combustion, and that is for 1 mole. That is in the definition. So over here there are 3 moles of carbon. So 3 times negative 393.5, I'll write like this. Then next is hydrogen. Hydrogen's enthalpy change of combustion is negative 285.8 per mole. There are 4, so 4 times negative 285.8. Oxygen can't be combusted. And then for propanol, I think the enthalpy change of combustion is negative 2021. Now what we'll do is we'll draw a cyclic arrow in such a way that it follows this arrow, the delta HR or the delta HF arrow. So I've drawn an arrow like this. This is the first part that was asking for an energy cycle to be drawn. In the next part, they're saying calculate the enthalpy change of formation of delta HF of propanol. So now you have to calculate this enthalpy change. So this arrow is following the cyclic arrow, right? So I'll write this as positive. This arrow is again following the cyclic arrow. I'll write this as positive. This arrow is against the cyclic arrow. So I'll write a negative over here and then write the value. Again, this arrow is opposite to this in direction, so I'll write a negative and then write this. And this will be equal to 0. This will always be equal to 0. So if you solve this, you'll get delta HF as negative 302.7 kilojoule per mole. And again, it's kilojoule per mole because the data was given in that form. I hope this question was clear. Now I have another question. In the previous question, let's just go back to it. We were given the enthalpy changes of combustion. In combustion, what happens is that when we combust carbon, hydrogen, or propanol, so carbon dioxide and water were formed, so that is why the arrows were pointing downwards. Now in this question, we have to find the delta HR of this reaction. I'm writing the equation first again. Over here, we have to find delta HR. We're given delta HF, the formation, the enthalpy change of the formation. Now for all of the molecules, we'll write all of the constituting elements over here below. So there's carbon, there's hydrogen, there's iodine, there's silver, there's fluorine. Now for CHI3 to be formed, some of these elements will be used. And to go from these elements to CHI3, because the definition for enthalpy change of formation is that 1 mole of the compound is formed, or the molecule is formed from its constituent elements. So the constituent element, that is 1 mole. So the energy change will be, the arrow will point upwards because it's going from here to there. So the energy change will be negative 182.1. Similarly, for AgF, for 1 mole, the energy change is negative 204.6. But over here there are 3 moles, so 3 times that. For CHF3, that is formed from 3 of these elements, the enthalpy change is negative 692.9, and for AgI, we'll have 3 times negative 61.8. Again, draw a cyclic arrow that follows this arrow. The cyclic arrow follows the delta HR arrow, so delta HR will come as positive. Now it's against these arrows in direction, it's opposite to them, so we'll have negative 692.9. Again, it's opposite to this, so negative 3 times negative 61.8. It's following the same direction as these arrows, so positive 3 times negative 204.6. And again, it's following this arrow in direction, so positive negative 182.1, and this is equal to 0, always equal to 0. So solving this, so delta HR is coming equal to negative 82.4 kilojoule per mole. So we'll do a few MCQs. In this MCQ, ethanol is increasingly being used as a fuel for cars. The standard enthalpy change of formation for carbon dioxide, water, and ethanol is given, and we have to find the standard enthalpy change of combustion of ethanol. So for this, I'll first write the equation for combustion of ethanol. So if ethanol is being combusted, carbon dioxide and water are formed. We'll balance this first. This is the balanced equation. Now we have to use the formation data to find the combustion Q. This is delta HC. Formation ke liye what we do when we have formation data, so what we do is we write the elements down here first. Then for ethanol, the value was negative 277. For oxygen, obviously there is no formation, it is an element. For all elements, the standard enthalpy change of formation is 0, because for an element being formed from an element, obviously there won't be any enthalpy change. Then for carbon dioxide, it will be negative 393 times 2. And for water, negative 286 times 3. Now I'll draw an arrow. Delta HC follows the arrow, so positive. This is against the arrow, so negative 2 times negative 393. This is against the arrow, so negative 286 times 3. And then this is following the arrow, so plus negative 277 equals 0. So if I solve this, so delta HC phi is equals to negative 1367 kilojoule per mole. That is option B. Then the next question, this is about finding the enthalpy change of combustion using the water's increase in temperature and all, using MC delta T. So in an experiment to calculate the enthalpy change of combustion of a fuel, 1.5 gram or 0. They've given the mole over here of the fuel was used to heat 200 gram of water. So there's 200 gram of water. Temperature change is 55 minus 25, that is 30, and specific heat capacity is given. So Q, that is MC delta T. M is 200, C is 4.18, and delta T will be 30. 200, 4.18, and 30. This gives 25080 joules. Now there is significant heat loss in this experiment, therefore the experimental value for the enthalpy change of combustion of the fuel will be different from the theoretical value. Using information above, what is the experimental value for the enthalpy change of combustion delta HC of the fuel? Okay. So now the enthalpy change that we found, 25080, that is for 0.0326 moles. This is 25080. For 1 mole, the enthalpy change will be X. So X will be equal to 25080 upon 0.0326. That is equal to 769325 joules. The answers are in kilojoules, so we'll convert it to kilojoules. This will be 769 kilojoules, rounded off. 2-3 significant figures. So 769 kilojoules, and because it's delta HC, that is combustion, and it's exothermic, so it will be negative, so that's why option B. 2. Solid sulfur consists of molecules made up of 8 atoms covalently bonded together, so it's S8. The bonding in sulfur dioxide is SO2, okay. Enthalpy change of combustion of S8 is given. Energy required to break 1 mole of S8 into gaseous atoms is given. Oxygen double bonds, bond enthalpy is given. Using this data, what is the value of the sulfur double bond oxygen bond enthalpy? So firstly, sulfur plus oxygen will give sulfur dioxide. Balancing this, I guess that's how we'll balance it. Yeah. Now we know that combustion is oxidizing 1 mole of the compound. Over here 1 mole of S8 is being oxidized, so that means that this reaction is delta HC of sulfur, and that is equal to negative 2376 given in the question. We know, so that is why we know the delta HR of the reaction. Delta HR, if we use this formula, delta HR equals sum of bond enthalpies of reactants minus sum of bond enthalpies of products. So delta HR we know is negative 2376. Now bond enthalpies of reactants में oxygen का we know that oxygen's bond enthalpy is 496 and there are 8 oxygen. So 8 times 496. What we have to find is SO2 में SO2 is basically like this, and we have to find the bond enthalpy of one of this bond. So there are 2 of these bonds in SO2, so total of 16 bonds over here. So over here we'll have some value for S8, and then negative, the reactants mein we'll have 16 times, if the bond enthalpy of this bond was X, then 16X. What we have to find is this, and then we're done. So bond enthalpy, when we did bond enthalpy, the definition that I gave was that it is the energy required to break 1 mole of covalent bonds into gaseous atoms. So this is, in other words, the bond enthalpy of S8. So 2232 will come over here. Now solving this, so 16x will be equal to 8576 divided by 16, so x is equals to 536. That is option B.